In this week's video, we're going to show you how you can defy gravity with objects you probably have already around the house.
If I told you you could buy your very own gravity distortion device at your local hardware store, you would probably think I was crazy, but you totally can. And not only that, it comes in multiple sizes, from small ones to medium-sized ones to even this 10-foot long one you see I have clamped right here. So what exactly do I mean by gravity distortion tube? Let's take this object for example. I'm going to hold it up beside our tube and drop it, and we're going to see how long it takes to hit the ground. 1.12 seconds. Now let's see the difference when we drop our object through our gravity distortion tube.
It is significantly slower. In fact, over 11 seconds later, you will finally hear it hit the tarp down below. Wait for it.
In fact, it takes so long to hit the ground that I can actually drop this through the tube, walk down the steps, all the way down the steps, and I don't even have to walk that fast. As you can see, I'm just taking my time. Plenty of time to spare. So what's the science behind this and how can you do it in your home with just a roll of aluminum foil? We're going to find out.
For this experiment, all you need are some neodymium magnets and a few copper rods. The good news is, if you don't want to go out and buy some copper rods, this experiment will still work with just some aluminum foil you have laying around the house. Copper rods come in various sizes and you can find them in any of your local hardware stores. The only thing to keep in mind is you're going to want it slightly thicker than the diameter of your magnet. So buy your magnet first because they come in various sizes as well, and then you'll know what size copper tubing to get. Our best results came when pairing a 1/2 inch diameter neodymium magnet with a 5/8 inch diameter copper tube. The first thing I did in this experiment was demonstrate to the kids that the copper is of course of metal.
Do you remember the phases of matter?
Solid, liquid, again.
And then I spend the next few moments demonstrating that just because it's a metal doesn't necessarily make it magnetic.
So they're not going to be attracted to it if I pull it together.
We'll see.
What do you think?
I don't think it will.
Don't think it will? You're right. They are not magnet. They do not do anything.
I was right.
You were right.
Yeah.
And then we timed how long it was going to take the magnets to fall from various heights off the table.
1, 2, 3, go.
All right, so about 0.3 seconds.
And then we did the exact same thing, but this time we measured how long it took the magnet to fall to the table when it was dropped from right beside the copper tube, just to confirm that the copper tube didn't exert any force on the magnet as it fell to the table.
3, 2, 1, go.
All right, so 0.58.
And that was indeed the case as long as you took into account our substandard scientific recording methods. And then of course we compare that to how long it took them to fall when they fell through the copper tubing to see the difference.
Now we're going to do it, you drop it through the tube.
And why is my son playing with his socks throughout this whole experiment? If you're a parent, you understand. There is no explanation.
Now we're going to do it, you drop it through the tube.
3, 2, 1, go.
3 seconds.
And there we have our experiment. Initially it took our magnets less than 1/2 second to fall to the ground, and now while traveling through the copper tube, it took them over 3 seconds to stick the landing. That's pretty neat. And just to add one more control, we dropped something of similar weight to the magnets down the copper tube like this battery, just to show that the slowing of the fall had nothing to do with the copper tube and everything to do with the magnets. After demonstrating the point, if you've picked up various tube sizes and magnets of different sizes as well, you can then do additional demonstrations, swapping out each tube with each magnet size, seeing the different effects each one has on each other. And don't forget, this experiment works exactly the same with a roll of aluminum foil if you don't want to go out and buy a copper tube.
So now we're walking out to see the experiments with the big pipe again.
Is it worth it to buy a 10-foot long copper tube for this experiment alone? No, that's why you keep the receipt and you take it back when you're done. You don't think Lowe's is watching this, do you?
If we drop this down from here, can we make it all the way down before it hits the ground?
If you run fast enough.
Do you think we have to run?
I think so.
All right, 3, 2, 1.
So I'm going to have to stop the video right here and remind you that my undergraduate degree was in chemistry and not workshop. The reason I say that is because the copper tube that I clamped to the deck may or may not have fallen off onto one of my children. I am happy to report that they are okay, but I promised them I would not be putting that into the video. And just in case you're wondering, we did make it down in time to catch the magnet. So getting back to the video, and more importantly the science behind it, let's try to explain what happens when these magnets seemingly defy gravity when they fall at a slower rate through a copper tube to the ground. So here we have our magnet, and we're going to let this represent our copper tube. When our magnet is falling through the copper tube, we have to keep in mind that it is bringing its magnetic field with it. And if you recall in our How to Make an Electromagnetic Train video, we talked about what the magnetic field looks like and how you can create it at home. So in our previous videos, we discussed how when electrons move, they create an electromagnetic field. And in today's demonstration, it's an example of how when a magnetic field passes through a conductor, it causes the electrons of that conductor to move. So now we have moving electrons that are creating their own magnetic field. And those magnetic fields are called eddy currents. Again, eddy currents are magnetic fields created by moving electrons through a conductor like our copper tube here, and that now gives us two magnetic fields, one from our magnet and one from the eddy currents created by the electrons. And as you can see here, when similar poles of a magnet are brought together, their magnetic fields oppose each other. A scientist by the name of Lenz said the same thing. Eddy currents will oppose the direction of the magnetic field that is creating them. So to bring it home, we have the force of gravity that is pulling our magnet down to the ground. And in this example, we now have eddy currents that are applying an additional force that is opposing that downward fall. And that opposition to the fall supplied by the eddy current certainly isn't enough to overcome the force of gravity, but it definitely is strong enough to slow our magnets down as they fall to the ground. So that's it for this week's video. It's a pretty complicated topic, but it is super easy to demonstrate at home with your kids. And I promise you they're going to like to see the effect of things falling down slower than they really should be. This is our third video on magnetism over the last few months. The worksheet from our previous video and this one will be uploaded to our website pretty soon. I hope you have a great day, everyone, and we'll see you next week.